Hello, students. In this lesson, we are going to learn more about machines. We are going to talk about simple machines and a little bit about complex machines. A machine is a device that multiplies force. A machine is a device that multiplies force. A machine is a device that multiplies force. Right? We have examples of machines. For example, a lever is a simple machine. We have pulleys. We have inclined plane and inclined planes. Those ones are also machines. In this lesson, we are going to focus on the two, a lever and a pulley. But I can tell you that complex machines are actually a combination of these simple machines here. Let's look at a simple machine such as a lever. I'll use a different color for that. So we know a lever can be used to lift heavy objects. So if I have a lever here, this is a lever. All right. Why am I doing this? I have enough space at the bottom. Okay. I believe I have enough space here. So let me do it here. Now drawing is hard. Okay, yeah. So this is the lever. And if I try to look at a different position, a different position can be drawn here. I'll use dotted line to show a different position of the lever. All right, I'm trying my best. Now, a lever, when you push it down with a force, this one is small force here. We call this force input. You can actually end up with a large force output. Force output. A lever in this case has moved through a distance, and this distance is distance output. So we write distance output. And as you can see, you have moved down through a longer distance. That will be distance input. So that's basically a lever, and the point of contact here is usually called a pivot, or the fulcrum, a pivot or fulcrum. Anyway, maybe it may just write a pivot. Some people will call that one a fulcrum. Okay, pivot. Now here, what I'm trying to see here is that I put in a small force, but then I get out a large force. You can see the arrow. Now I'm not getting a large force output out of nothing, but I had to move through a longer distance here. And the load, if it was placed a load here, the load actually will move through a shorter distance. So if we ignore air resistance or any opposing forces, friction at the point of contact here, if we ignore the weight and balance the force of the weight of the lever, then we can say that if all things, are taken care of, then we should be able to conclude to say that the work input must be equal to the work output. We're doing this because of the conservation of energy. We can't just get more work output than we put in. That's impossible. So what I'm trying to say that if I multiply the force input times the distance input, that's the work input must be equal to the work output times the distance output. This assuming that there are no losses. We are going to see later on in this lesson what happens if there are if friction is taken into consideration or air resistance is taken into consideration in this kind of machine. Now, to make sure that we understand that a machine really multiplies input force, we can write the input force being small and distance is actually bigger. Distance is bigger. Let me just write a bigger D. I'm trying to visually show you that indeed the force input is small, whereas the distance is bigger. That must be equal to a larger force. I'm writing a big F here in a small distance. So this equation should remind you that indeed a machine multiplies input force. For a smaller force here, I get out a bigger force. So you can actually lift a large rock that you are unable to lift by yourself. By using a lever, a smaller input force here turns out to produce a large force output. One thing you should know is that a machine multiplies input force at the expense of distance. I think I mentioned this already. You moved through a longer distance here, but the load, whatever you are lifting, only rises a little bit. As you can see here, it's a smaller displacement upward. So a machine multiplies input force at the expense of distance. Okay, so I don't know if I write that. So the use of the lever multiplies input force at the expense of distance. So let me write it here. The use of a lever as a machine multiplies force at the expense of distance. Okay, now let's look at a different machine, and this one is a pulley. Pulley is a simple machine. It's used oftentimes at construction sites and in several devices or several equipment. They use actually pulleys. I'm going to draw my pulley here. Simple pulley, because pulleys come in different scenarios or different complications. Mine here will be very simple, just to drive the point home. Let me draw a nice line there. Okay. Like to draw good lines, but time is an issue always. Okay, so I have my pulley here. It's always nice to see it in person, but videos can help also. Video here, and then we have another pulley here. Yeah, and we are going to have a cable. Let me use a different marker. So there's something that goes through here. That's the thread, and goes like this, and you pull here. That's a pulling part. This is connected to the wall, and this is connected to whatever you're lifting, maybe a weight. I'm going to put 400 newtons here, 400 newtons. All right, so when you pull here, let's say you're putting in force input here. So putting force input by pulling down at a constant speed, then this is what happens. We have 400 newtons acting downward. Therefore, there has to be 200 force in each rope here. So 200 in this rope, that will be the tension in this rope. That will be 200, and there will be 200 in this one also. So 200 in this tension and 200 in that tension. And the force you are putting in here has to be also 200 newtons, because if you follow the line, the 200 newtons line, this line, if you follow it all the way here, follow it, you see that you are going to require 200 newtons to pull also. Yep, so what I'm trying to say here is that you only require 200 newtons to pull a load that is 400 newtons. That's a machine, because you're actually using a smaller force to do more, to lift something that has more weight, right? So a machine multiplies input force at the expense of distance. In this case, this looks like the machine is multiplying input force twice, as you can see. Now, imagine if the crate rises by 4 meters. So if the crate rises by, let's say, 4 meters, right? Then potential energy will be gained. The potential energy gained will be equal to, remember, potential energy gained is mgh, and the mgh, the mg alone is the weight which is 400. So that's 400 newtons. Mg is the weight and the height is 4 meters. In this case, the potential energy gain in this problem, let's write this. Potential energy gain is going to be 1600 joules of energy. Now, for an ideal pendulum, if the pendulum is ideal, we ignore friction and air resistance. For an ideal, not pendulum, but pulley, For an ideal pulley, we see that this potential energy gain must be equal to the work done by force in, must be equal to work done by the pulling force or whoever is pulling there, which is equal to work energy expended in pulling, which is equal to energy expended in pulling. Energy expended in pulling, right? If the pulley is ideal, then the potential energy gain here must be equal to the work done by force in, this force here, this force, the work done by the pulling force, which is equivalent to the energy expended by anybody who's pulling the rope downward. If you are pulling at this point, the work that you do is the energy you expend. And that translates to the potential that will be gained by the crate in rising through 4 meters. So here we see that again, we can do the same thing here. The work input will be equal to the work output. Or we can write this as the force input times distance input is equal to force output times distance output. All right, that's what we see there. And therefore, we can find the distance input. In other words, I would like to know if the box rises 4 meters here, how long can I pull the rope? So distance input will be force output times distance output divided by force input. That will give me, remember the force output is the 400 newtons. That's the load I'm lifting. The distance output, we are told that is 4 meters, and you're dividing by force input. Well, we just analyzed here and we found is 200 newtons. In this case, you're going to find distance input as 8 meters. So what it means is that you need to pull 8 meters of the rope, although it only rises by 4 meters. So you pull 8 meters of the rope, but it only rises 4 meters. You pull 8 meters of rope, but only rises by 4 meters. All right, that's what we see there. But remember, in a machine multiplies input force at the expense of distance. Well, you were able to benefit because you use the smaller force of 200 here, a smaller force of 200, but then you have to be ready to pull for longer distance, a longer distance of 8 meters, whilst the box only rises by what? Only rises by 4 meters. Excuse me, did I lose anything? Oh, almost lost everything. Okay, yeah, so that's the pulley here. That's the pulley. Now let's look at the concept of efficiency. Let's look at the concept of efficiency of a machine. Efficiency. So efficiency just tells us how good a machine is in terms of multiplying the force, how good a machine is in terms of multiplying input force. By definition, we are going to define efficiency as the useful energy output, useful energy output. We're going to divide that by total energy input. So for an ideal machine, as we have seen, we ignore friction, air resistance, the useful energy output is equal to total energy input. So ideal machines have efficiency of 1, or which is actually 100%. Yep. So for an ideal machine, we see that input energy, the input energy is equal to output energy, and therefore efficiency is actually equal to 1, or you can also write 1 as 100%. 100% and 1 are the same. If you treat 100%, is just like 100 over 100, which is 1. 100% is equal to 100 divided by 100. A percent is per 100. So this is also 1. So the efficiency will be 1 or 100%. That's for ideal machine. But let's look at this example. Say while using a lever, you do 1,000 joules of work, and get out, let's say you get out 900 joules of work. That's possible because we have actually now taken into consideration the effect of friction and air resistance. So in the end, you end up with 900 joules of work, but you put in 100 joules of work. Of course, we are not saying that we are violating or disobeying the principle of conservation of energy. What we are saying is that some of the energy in this process is transformed into other forms of energy, like thermal energy, sound energy. But the efficiency, which I will just call E, will just be useful energy output according to the formula above. The output energy there will be just 900. So 900 joules divided by, you are putting in what? 1,000 joules. The result here will be actually 0.9. And 0.9 can also be written as 90%. 90% is the same as 90 over 100, which is 0.9. So 0.9 or 90%. That will be the efficiency of this kind of lever. So what it means is that 10% of input work transforms into thermal energy. 90%, good. But we are missing 10%. That missing 10% of the input work transforms into thermal energy or other forms of energies. That's the concept of efficiency. Most of the machines, when they are designed, it is very important to talk about efficiency. We can talk about efficiency of the engines that we use at home. We can also talk about efficiency of cars. If you design new cars, customers will be interested in knowing how efficient is your car in terms of converting gasoline into kinetic energy? How much energy is disposed? How much energy is useful? So those are the questions of efficiency, very, very important, because they tell you whether you should invest in that machine or not, or whether, it's profitable or not. All right, so I think I'll stop here. In the next lesson, we are going to discuss the sources of energy. That will be our last lesson. We're going to talk about sources of energy. I was about to include that in this lesson, but I feel like it's going to be a little bit longer. So I'll stop here. But remember, just a summary, we have learned that a machine is a device that multiplies force. We have examples: a lever, pulleys, and inclined plane. We haven't discussed inclined plane, but an inclined plane is a machine also. Here, we have seen that a machine multiplies input force at the expense of distance. And we have seen here an example whereby we're moving through longer distance and we get out a large force, but the other side moves a little bit. We have seen a pulley as a machine. For this kind of pulley, actually you're benefiting because you're putting only 200 newtons, but you are raising a 400 Newton load. What you have seen here is that whilst the load rises only 4 meters, we have seen that you need to pull the rope. You have to pull the rope 80 meters distance, so you're multiplying the input force at the expense of distance. That's very, very important. And since it's a zero machine, we can actually apply this equation. If it's not, if we take care of friction and that, then we have to be careful how we apply this equation. And we talked about efficiency of a machine. It's just useful energy output divided by total energy input. As we can see, if it's a machine is ideal, just like we have seen with the lever and the pulley discussions, if it's ideal, then we are going to have a machine being 100%. And as we can see, there's no machine that can be 100% efficient. There is always some form of energy that will be transformed into other forms of energy. All right. Okay, so this marks the end of this discussion. If you have questions, please let me know. Bye for now.